Hello, I'm Maria Cardes. In this video, I will show you how NIR spectroscopy works. Near-infrared light, NIR for short, lies in the wavelength range of 780 to 2,500 nanometers. NIR spectroscopy is based on the absorption of NIR light by various atomic bonds, which is then used to characterize different materials. For example, the OH bond vibrations are used to determine the moisture content in samples. The more moisture in the sample, the more NIR light is absorbed in the specific wavelength region. With NIR spectroscopy, different samples, like solids, liquids, and creams, can be analyzed. Depending on the sample type, a different measuring method is used. For the analysis of liquid samples or suspensions, the sample is placed between the NIR light source and the detector. NIR light is transmitted through the sample, and any unabsorbed light is detected by the detector. This measuring mode is known as transmission. Solid samples are typically measured with the diffuse reflection mode. The NIR light penetrates into the sample and interacts with it. Parts of this light are absorbed while unabsorbed NIR light is reflected back to the detector. The transflection mode is most suitable to measure creams, pastes, and gels. This mode combines transmission and reflection. A reflector is placed behind the sample, which reflects any unabsorbed NIR light back to the detector. Now, you know the basic behind NIR spectroscopy. But how do you get results from the measurement? For this, a mathematical model, called prediction model, is created. To create such a prediction model, we need the absorption spectra of our sample on the one hand and a reference value on the other. For our moisture example, we can use Carl-Fisher titration to get the reference values. Whenever an unknown sample is measured, the model predicts the content of interest, in our example moisture. Choosing the right measuring mode and having a robust prediction model for your sample are the most important points to consider when developing an NIR operating procedure. To make your life even easier, Metrum offers ready-to-use precalibrations to determine important quality control parameters for different industries. For example, polymers, polyols, fuels, wood pulp, palm oil, and many more. For more information, visit metrum.com or contact your local sales representative for a demo. Thanks for watching.
To prepare a solid sample for the IR, you will need the potassium bromide located in the desiccator. The first step to preparing your sample is to zero the balance with an empty weighboat. Measure out approximately 100 milligrams of the potassium bromide into the tared weighboat. We initially had too much and had to remove some of it to get the correct amount. You should do the same to get as close as possible to 100 milligrams. Once you get the 100 milligrams, then place the measured potassium bromide off to the side. Next, zero the balance again with a new weighboat. Measure out 0.1 to 10 milligrams of your solid sample. place this on the balance and record the weight. It is important that you do not exceed 10 milligrams, and ideally a smaller amount of the sample is best. Set your sample to the side with your measured amount of potassium bromide.
Combine the measured amounts of potassium bromide and the sample into the mortar. Use the pestle to grind the two solids together. Do this for about 20 seconds so that both solids are mixed evenly and ground well. Next, to prepare the bolt, screw in the bottom screw, being careful not to over-tighten. Transfer your sample from the mortar to a third unused weigh boat and then into the open end of the bolt. Secure the top with a second screw. Move the bolt to the clamp and secure in position. Using a torque wrench, tighten the top bolt until you hear a click and the wrench goes no further. Set a timer for 1 minute and let the bolt sit until the timer expires. Rotate the top of the torque wrench in the meantime so you can unscrew the bolt later. Place back on the screw and bolt and push until the bolt releases. Keep rotating until the top screw is removed. Loosen the bolt from the clamp and hold in your hand. Unscrew the bottom screw.
Tap the sides of the bolt on the lab bench to remove loose particles. Walk your bolt over to the IR and place inside, making sure that the opening is exposed on both sides and can allow the beam to pass through. Turn the IR on and make sure a background scan has been run without the bolt in the machine, and then hit scan. Your spectrum will be produced. Luckily, liquid sample prep is much easier. To prepare a liquid sample, take the salt plates from the desiccator. Then rub the salt plates on the surface to clean them. Once cleaned and dried, place a drop of your sample on one of the salt plates. Place the other salt plate on top of the one containing the drop. Walk over to the IR and make sure that a background scan has been run with nothing in the way of the beam. Then, place your sample so that the beam is able to pass through it. You are now ready to scan. Your spectrum will be produced by the machine.
To clean your used salt plates, douse them with ethanol on both sides and rub again on the surface. Do not wash with water. Also, be sure not to touch the surface of the salt plates, only touch them lightly on the sides. Repack the salt plates in their containers and return all of the materials to the desiccator. To clean up from a solid sample preparation, wash the bolt and screws with water and acetone. Then place all materials in the drying oven along with the cleaned mortar and pestle. After an hour, return all materials to desiccator for others to use.
For running a sample, it's important that we take a background first. This will eliminate any peaks that are due to the instrumentation or film on the windows. To take a background first, you have to clean the crystal. So we're going to use IPA. We want to squirt the IPA on the chem wipe first, then you'll clean the crystal in an outward fashion, and then go ahead and dry it using a dry clean chem wipe. Once the crystal is clean, you can go ahead and take a background. To take a background, you will click the background button. The background is saved in the background of the software, so you won't physically see it on the screen. Next, you're going to want to collect your sample. Make sure that you're putting a sample ID in the sample ID box before you run it. To collect a sample, go ahead and place that sample on the crystal. And apply pressure. You can go ahead and click the scan button and it will go into preview mode. In the preview mode, you'll notice a force gauge at the bottom of the screen. Make sure you apply enough pressure to be able to get a good spectra on the screen. This is usually around 90 force. You'll see some good peaks show up. Once you have a good spectra, go ahead and hit scan again. Scanning again will actually start collecting the data. Now that you have the data, you may want to run a library search or a compare. To run a library search, go ahead and hit the search button. The library search is going to run. The more items in your library, the longer the search takes. And your search values will all show up on the right-hand side of the screen. So for this one, the top search is polypropylene, and the standard we ran was polypropylene.
What are the major differences between infrared and near-infrared spectroscopy? Hi, I am Dave van Staveren. In this video, I will briefly explain the differences between mid-infrared spectroscopy, IR spectroscopy for short, and near-infrared spectroscopy, otherwise known as NIR spectroscopy. Both IR and NIR are vibrational spectroscopies, meaning that parts of the molecules will vibrate when absorbing light at specific wavelengths. As the names imply, IR and NIR spectroscopy use different spectral ranges of light. This wavelength variation results in three key differences: the required sample size, penetration of the light into the sample, and the resulting spectral information. Let's look at the first difference, the sample size. Vibrations in the infrared region are classified as fundamental vibrations. As such, they have a higher probability of occurrence than overtones and combination bands, vibrations happening in the near-infrared region. Therefore, infrared light is absorbed more strongly than NIR light. Because of this, small sample quantities should be used with IR spectroscopy. Sample preparation is often required as well. For example, needing to press a potassium bromide tablet or prepare liquid dilutions. Conversely, the absorption of near-infrared light is much weaker and samples can be measured as is, without any sample preparation needed. In addition, longer path lengths can be used when measuring liquid samples with NIR spectroscopy. This is especially useful for online measurements in industrial process environment. Now for the second difference between IR and NIR spectroscopy, the sample penetration by the light. Often, it is only possible to collect information about the surface of a sample when using IR spectroscopy. NIR light, on the other hand, is of higher energy and therefore penetrates deeper into the sample. This makes NIR spectroscopy the ideal choice for studying heterogeneous samples, as information can be collected from a larger sample area in this situation. Finally, the third major difference, the spectral information. IR spectra are suitable for identifying functional groups within a sample, as well-defined, sharp bands are observed for various functional groups. In contrast, bands in NIR spectra are much broader. This makes identification of functional groups more difficult. The benefit of these broader overtone and combination bands is that you can also quantify chemical and physical parameters of the sample. For this quantification, mathematical models called prediction models are required. To summarize, IR spectroscopy is well suited for the identification of substances. However, sample preparation is usually needed, but can be time-consuming. Also, the analysis of heterogeneous solid samples is a challenge for IR spectroscopy. On the contrary, NIR spectroscopy can be used for the identification of molecules and quantification of chemical and physical parameters without needing any sample preparation. Because of the increased penetration depth of the NIR light, the analysis of heterogeneous solid samples is also possible. When dealing with liquid samples, longer path lengths can be used for NIR spectroscopy compared to IR spectroscopy. A strong argument for using NIR spectroscopy for online measurements in industrial process environments. For more information, visit our website or contact your local Metrome specialist. Thanks for watching.
Hello everyone, my name is Abigail Poe and I'm a research associate here at NCPTT. I'm welcoming you into our lab today to talk about this instrument here, which is the FTIR, or Fourier Transform Infrared Spectroscopy. So this instrument can be used to help us identify compounds by looking for functional groups that are contained in them. So if we break it down, the FT part, Fourier Transform, stands for a mathematical technique that takes the raw data and converts it, along with the help of a computer, into meaningful spectrums. On the other hand, the IR part stands for infrared spectroscopy, which is the type of light that this instrument uses. And it also is the molecular vibrations that the light produces as it interacts with the compounds. So we can use this instrument for a lot of different techniques in our lab. So we can look for identifying unknown compounds or materials, as well as surface contaminants, or we can look for how deeply these chemicals penetrate into the substrate itself. So like for my project specifically, I'm studying how herbicides affect the properties of historic stone and masonry materials. So one of the tests that I'm using with this is, in addition to looking at whether there's herbicide residues left on the surface, I'm interested in seeing whether any of them have penetrated into the material itself. So I'm performing a test with this to see if the artificial accelerated weathering process pushed the herbicide into it and how deeply that penetration occurred. So as you can see, we can use this instrument for a host of tests that tell us a bunch of useful information. So now I'm going to start talking about the two different components, the first being ATR, which is this one right here. ATR stands for attenuated total reflectance. So this test can be used for solids and liquids. If we use it with solids, it's typically a destructive test because it requires us to powderize the sample, like you can see I've done here. So the liquid or solid is placed onto a crystal, which we have here. A beam of infrared light is passed upwards. It interacts with this material, and this interaction produces a spectrum of the absorption of that light. So that spectrum reveals useful things, again, like the functional groups and other information we can use in identifying the compound. So this test is relatively simple to perform because it doesn't require a whole lot of sample prep, and it's fairly consistent in the results that it gives us. On the other side, we have an IR microscope. The IR microscope is useful for both, mainly solids is what we use it for in our lab, like this piece of granite that I have here. It can be used for non-destructive tests and letting us just take the sample as a whole and looking at things on the surface, or we can also cut a sliver off and test for things like the depth of penetration that I was talking about earlier. So the microscope actually uses liquid nitrogen, which I'll be demonstrating in a little bit, to help keep it cool and prevent it from overheating as we're running these tests. So I'm going to be showing you how to use the ATR with this limestone sample that I have here. Like I mentioned, when we have a solid like that, we typically powderize it. So I've got some powder that I collected earlier in here. And it doesn't really take much. Close this handle right here, so basically we're now ready to take the IR spec, so that ensures that we have contact of the powder with the crystal itself. and I press that button there so we can run and get the spectrum, which you'll be seeing on the computer later. So now I'm going to be using the microscope, and the first step that I'm going to be doing is adding the liquid nitrogen. So now we're going to be looking at one of my granite samples under the microscope. So this test is specifically looking for whether the herbicide is on the surface of this sample itself. I'm just focusing the light source right now and making sure it looks clear in the microscope before I collect my sample. So now that I've got it sufficiently clear, I'm going to go ahead and run the microscope, which will collect the spectrum that we'll see on the computer later. So now that we have our spectrum, we come over to the computer where we're going to analyze them, and you can see here a couple of representative spectrum that are produced from some of my earlier samples. But I'm specifically going to be focusing on the limestone one itself, so I'm going to switch over to that really quickly. So basically, we have a program on our computer that's filled with reference libraries. So what that does is it compares our spectrum to spectrums that we have from other software or spectrums that we've added from known substances, known chemicals, and it looks for matches in our spectrum to those. So I'm going to run this one through this to see if we get any matches. And again, this is our limestone sample. And it doesn't really take long to do this. As you can see, it's already done. It's going to pop up matches. And so if we look on the list, our actual first match is calcium carbonate, which we know is in limestone. So it has identified one of the components in limestone. So you can see this is very helpful in helping us identify what groups are in the materials and the chemicals and the substrates that we're using, so that we're able to identify whether, again, like I said, there's contaminants, or maybe like for my project, herbicide residues left behind. Or if we have an unknown material, we can also try to identify it this way. So that's pretty much it. You can see this is a pretty useful instrument in the lab. And I guess I'm going to get back to analyzing the rest of my samples, but it's been a pleasure to show you a little bit about this instrument. And if you want to find out more about this one or the other ones, you can visit our website and our YouTube channel where we have several videos. Thanks for watching, and if you have any questions, put them in the comments below and we'll be glad to answer them. Thank you.